We're going to practice some graph sketching, but we have to use calculus according to the question. Previously, we could solve and sketch this question using simple factoring and not even using calculus, but let's try to force ourselves to use calculus just for the sake of practice. So calculus, we're interested in derivative. So let's find f prime of x. F prime of x, use power rule, 2 times 3 is 6. We decrease the exponent by 1. Negative 8 times 2 is negative 16. X to the 1, I'm not going to bother writing down the 1. And then focusing on this third term, we're going to simply copy the coefficient, which is plus x. So this here is the derivative, or the slope, of this polynomial function. So in calculus, we're interested in setting the derivative equals 0, because that has a lot of meaning. The slope is 0. When? So let's factor out some number here. Let's factor out a 2. So this is 2, and we have 3x squared minus 8x plus 4. So we now have a trinomial here that we can factor. But if you really want, using algebra, you can divide both sides by 2. By dividing both sides of this equal sign by 2, we have 0 is equals to 3x squared minus 8x plus 4. Now we're going to factor this. This trinomial can be factored to 3x minus 2 and x minus 2. Something times something equals 0. So where is the derivative 0? The derivative is 0, or the slope is 0 at x equals 2, the opposite of negative 2 equals 2, or we're going to say that this factor, 3x minus 2 equals 0. Just using basic algebra, we say that x equals 2/3. So the fast way of figuring out the actual root, or the value in which we're interested in, is figure out the opposite of negative, which is positive, and take this number, this divided by the coefficient of x, 2/3. So that's the fast way of doing it. Okay, so these are very, very important critical points. The critical points are found where the slope is equal to 0. So using your previous technique of just factoring this polynomial, we don't even need to use calculus whatsoever. We can do a rough sketch. But what we have here is we have a graph, and we know that if this is 1, 2, 3, this is just a nice xy axis graph. At x equals 2, this dotted line here, we have something interesting happening. We have we have a slope of 0, which could possibly be a maximum, or could possibly be a minimum. It could possibly be neither. And we have x equals 2/3. So 2/3 is a bit less than 1. It's around here. So I'm going to just draw a little dotted line here and have a little boundary. Without using some other techniques, we're kind of lost as to the overall shape of this graph. You could use some reasoning. You could say that the overall polynomial is dominated by the most powerful highest degree term, which is x cubed. And we know that cubic functions look like this. Memorize that as a base x cubed cubic function. And there's no negative sign here, so the graph's not fixed. So we know that somehow the graph is tending up to down. That's some basic knowledge that we have. But just focusing on this critical point, the slope being 0, let's think of a nice technique and strategy to sketch this type of graph. So where the slope is 0, and we have the boundaries at x equals 2 and 2/3, we're going to call these country boundaries. These are critical points. Think of this to the left as Canada. Think of the middle as USA, and think of the right as Mexico. We have these border walls. At these critical points, there is a potential change in concavity. So right now we're interested in figuring out the slope f prime of x equals 0. Now where did this occur? It could occur at a maximum. Suppose the polynomial has a little bump here like a mountain. If the slope here is a maximum, you can see here this is the maximum. You're on top of the world, you're on top of Mount Everest. this is very important because your critical point here states that this graph should be increasing and decreasing. Now another scenario is the graph has a minimum. So we attack this minimum because the derivative here is 0. This is also a very important point. So in this case, the graph is decreasing and the graph is increasing. Now who knows? You cannot assume just because the derivative is 0 we have a maximum or minimum. The graph could be perhaps x cubed, a cubic function. It could look exactly like this. In this case, the derivative is 0, but the graph here has neither a minimum or maximum. This here is called the point of inflection, where you have a change in concavity. So please don't assume that just because the derivative is 0, it's for sure a maximum or minimum. Let's try to reason it out here. So right now, we actually calculated the formula for the derivative, which is f prime of x equals 6x squared minus 16x plus 8. So why don't we have a test point? We have 3 countries. The critical points are determined by the derivative equals 0. The critical points are also determined. We have to set up another country wall if the derivative is undefined. Now for this question here, the derivative is never undefined. It's defined for all real numbers. This here happens to be a parabola. So let's not worry about that for now. Let's just test the country here. So in Canada, let's test a nice Canadian citizen, which is here. Suppose we're going to test this point 0. 0 for sure is a Canadian. They're in this land here. And so what is the slope? What is the slope? Question mark. What is f prime of 0? Question mark. The slope happens to be, substitute 0 into here. It's going to be 6 times 0 squared minus 16 times 0 plus 8. 0 times anything is 0. This becomes 0, and there's 8. So the derivative is 8. When we say that the slope is 8, that's increasing. So we're going to just draw a nice line here. It doesn't have to be an actual slope of 8, but we just want to emphasize that the function is increasing. We climb the mountain left to right, and we're increasing. So draw a nice stick. Now let's pick a nice US citizen. So between here, between these border walls. Nice US citizen is a number 1. Why am I not choosing 1.1 or 1.1469? Is because 1 is a nice integer. I can see it right away. For sure, the number 1 is a US citizen. So let's find the slope for this 1. What's f prime of 1? So f prime of 1, let's just focus on the derivative formula here. F prime of 1 is equals to 6, 1 squared minus 16 times 1 plus 8. We have here, this is going to be 6 minus 16 plus 8. And as you can see, 6 plus 8 is going to be 14. 14 minus 16 is going to be negative 2. So we don't really have to calculate all the numbers. All we know that for sure is that the slope is going to be negative. It's going to be negative, so therefore the graph is going to be downhill. So this is amazing. Even though we only have information about the derivatives and we have a very primitive stickman type drawing of the actual graph, the shape, whether the graph is increasing or decreasing, we can kind of figure out that when you have a stick going up and down, we call this a local max or a maximum. When 2 sticks go like this, it's maximum. When 2 sticks go like this, it's going to be called a minimum. When 2 sticks are going this way, this could be a point of inflection. Alright, let's try this last country here. So anything to the right of this number 2 is going to be Mexico. So let's pick a nice candidate. Can you read my mind what number I'm going to pick? I'm going to pick 3. You could have picked 4 or 5 as well, that's fine. So let's try 3. What's f prime of 3? It's going to be the derivative formula here that we figured out previously. It's going to be 6, 3 squared minus, I'm just using substitution now, 13 plus 8. And these numbers are getting quite big. You can use a calculator if you have one. 3 times 3 is 9, 9 times 6 is 54, minus 48 plus 8. So right away you can see this is going to be positive. I'm not going to even bother calculating it. 54 plus 8 is some big number. It's going to be 62 minus 48. It's going to be positive. If you really want to work it out, you can do so. So bottom line is the slope is positive. So I'm going to just draw a stick here. And again, we have a nice valley. So therefore this is called a local min. We have a local minimum at x equals 2. So we just drew a nice stickman drawing, and we came to the conclusion that there's a local maximum at x equals 2/3 and a local minimum at x equals 2. Now what if you want to actually find the coordinates of the max and the min? So this is where you need to substitute this value back into the original function, not into the derivative, not f prime of x, but into the actual f of x formula, because we're interested in the actual value. So we're going to say f of x, or f of 2/3, is equals to 2 something cubed minus 8 something squared plus 8 times that something, and that something happens to be 2/3. So similarly, you can find the actual y coordinate of the local min if you plug in 2 into the f of x, into the actual function, not the derivative function. So it would be 2 something cubed minus 8 something squared plus 8 something, and we're going to substitute in 2. So let me just show you what Desmos looks like at this point. So here's the actual function. We try to sketch this using calculus. Y equals that, and we figured out the derivative is 0 here and here, and in order to calculate the actual y value, such as 2.37, you have to plug in 2/3 or 0.666666 into the original function, and that's what the result is. Now this y value is so clean and simple, 0. Why don't we just work it out slowly just to see what that looks like? So here we have a local min at x equals 2. This f of 2 is the y value, and we're expecting it to be equal to 0. Let's work it out slowly. 2 cubed happens to be 8. 2 times 8 is 16. This is going to be minus. 2 squared happens to be 4. 4 times 8 is 32. And then we have plus 16. As you can see, 8 times 2 is 16. 16 plus 16 is 32. Minus 32 is 0. So the results are as expected. It's amazing how we can use calculus to sketch graphs. And we can also use other techniques as well, such as factoring. Please use the easier technique.